If you have rotation about a fixed axis, then you can say VR is equal to R dot, and in that case, R dot doesn't change. So you're going to see a lot of problems where you have a pinpoint, it rotates around, and V sub R is equal to 0. V theta is equal to R theta dot, or V equals R omega. If you continue, you also can do the same thing as we did in chapter 2 with constant acceleration, and you end up with these equations right here. Omega equals omega naught plus alpha ct, theta equals theta naught plus omega naught t, 1/2 alpha ct squared, and omega squared equals omega naught squared plus twice AC theta minus theta naught. And you can see sort of the corresponding parallel terms here for each of them. Or sorry, bump, bump, bump. That's okay. Oh, no. Yeah, okay. So you can write all of this out. Now, the one funny thing in this course, and the reason why you stick it out for another 3 years after this, is that we only do planar measurements, or planar modeling. And so when we look at the equations of motion here, we have bodies, rigid bodies, that translate within the plane of the screen. They don't move in and out. And because they don't move in and out, they only have minus omega squared r. This is a good opportunity to sort of get up to speed with any cross products you want to do. But if you just put r is I in j and omega is in k, you'll find immediately you can't help but get this relationship right here. But this relationship doesn't hold true, and in third year when you start doing robotics and things like that, it's better to use the vector formulation. But for now, this does. Okay. Acceleration tangential, everybody loves it. Alpha times r, so it's going to be dependent on the angular acceleration here. Normal acceleration minus omega squared r. So you're writing and looking at terms a little bit differently, but it's still the same sort of expressions as before. General plane motion, we take the translation and the rotation and add them together. So essentially, a body that's sort of doing this as it's moving is going to do this mathematically and rotate into position. So VB or VA is equal to VB plus VA with respect to B, or the other way around, depending on what you want to write. VA with respect to B is R omega. VA with respect to B, omega cross R, and R is the RAB. This is not hard at this point because you're not really doing anything. We're going to do more analysis of accelerations, but accelerations are very difficult to visualize. I tend to sort of bias towards a vector solution for everything in this course, but different people have different approaches. So just be aware there are a lot of different ways to do things. However, the ground rule in all of these problems, especially now, is draw them out. Draw the vectors, make sure they make sense. As before, acceleration A equals acceleration B plus acceleration A relative to B, acceleration A equals acceleration B. But now you're going to take the acceleration of A with respect to B and include a normal and a tangential component. And when you do that, you have two different approaches. So you're going to end up with a scalar approach where the signs don't matter. And the reason why the signs don't matter is that you are drawing the solution out, and as you draw the solution out, you decide which direction things should happen. So if it's positive, it's negative, you'll fix it later. However, if you are doing it with a vector approach requires you to know what exactly the directions are. And so when you do normal acceleration, you do have to include minus in this term. So the difference in approach, you can be a bit sloppy, with scalar/graphical approaches. But if you are, you have to know exactly what the directions are at the end. Tangential direction, alpha cross arc. So that's all of chapter 5, by the way. So where was I? So I'm going to do a couple more examples. And one of the things that's really helpful at this point, so in terms of the quiz, or sorry, the midterm on next Thursday, we only cover up to velocities. You are free to do whatever you want to. I did add one thing, because I realized in the middle of the lecture I probably didn't define things as clearly as I should, so that if you want to do this later, you will get it. Oh, and other thing, these notes, I'll probably not post them until tomorrow. I don't think there's that much of a rush. I'd like to do it as 3, not as 2, and 2 plus 3. Okay. This is always good to know, okay? And you're going to end up doing a lot of cases like this. Yeah, it's good to know this. You need to know where your point of contact is and where your rolling without slip is occurring. And if you look at some of the older, probably older final exams, more so than the midterms, but some of the older midterms too, we do talk a lot about rolling without slip. And when we talk about rolling without slip, we often will put a figure like that and say, okay, where's, solve it. You just need to sort of remember these sorts of things here for now. It's more interesting when dealing with kinematics. So yesterday, there we go. So yesterday we had solved through it, and I had solved it using a vector approach. Now that was a little bit fast, and I know it was fast. We were right at 258 or something. So there are different ways of approaching it. I'm going to do the second way in a moment, or third way in this case. The first way was the absolute motion, where you use the geometry of the motion, everything is solved through for, and it all works out really well, but it's really only good for specific cases. However, for this one, I ended up doing it as a vector approach first, and the only thing that I really needed to know was one velocity. I didn't really do anything with it. I got my omega from it, which was 10 rads per second k. And one of the important points here is that the rotation, if it's rolling without slip and it's moving forward, it has to be rolling in the clockwise direction. And if it's rolling clockwise, then it's a negative value. Then over here, I didn't write. Oh, I did. Okay. So then what I had to do was say, hey, I have velocity of A, and velocity of A is equal to velocity of O, which I'm given at the beginning of the problem, plus velocity of O with respect to A, or A with respect to O. And I came up with these great results, and I never showed you why, but that's point O, that's point A, that's RA with respect to O, RA with respect to O in the y direction, and RA with respect to O in the x direction. So I was given in this problem that RA is equal to 200 millimeters. And if I know that, and I know what my coordinate directions are, and again, coordinate directions with vector solutions have to be defined. Really not a good idea to solve these too quickly. And one thing that you'll notice is that this is A with respect to O, which means that the y direction is in the positive sense, but the x direction is negative. And you'll notice that that sort of is, I don't want to do dots. That's why I have a negative cos theta and a positive sine theta for those two terms. The reason I keep pushing on the vector solution is that if you draw the diagram you're dealing with and you keep consistent to the notation, then you'll be a lot better off. And I'll make that a negative. Okay, so here is the last approach. Any questions on that one? So as you kind of go forward with all of this stuff, the third approach is a scalar or graphical approach, as I tend to call it. And with a graphical approach, what you're doing is you're going to start looking at the same problem. So here, I'm going to put out all of the various radial directions. So in red, you see a line that connects C to A, a line that connects C to O, and you see an x-axis and a very small y-axis there. So V sub O, the V naught is 3 meters per second. You're given that at the beginning of the problem. And you can find omega. Now, that's the same omega that I just solved for. So in the two parts of this problem, what you'll notice is that I'm not getting new answers. I'm just getting sort of the same thing again. Now, if I do that and I want to solve for V sub A, so all I really wanted was this. And this is R. So there you go. I can write VA equals VO plus VA with respect to O. All that. And if I do that, I can start by saying, okay, VO is equal to this, which is given. So this is that part of the solution. But for VA with respect to O, I need to know the direction of the rotation. And I know that in order for a rotation to occur, that rotation or that velocity vector has to be normal to that vector. So normal. And I can calculate, I have a triangle here which is kind of pretty good. I have the initial theta, which was 30 degrees. I get theta equals, beta equals to 60 degrees. And if I want the magnitude of V sub A, I'll end up with the same magnitude. So that works out really well, and everything's sort of super. The other thing that I could do is choose a better point. And so if I choose a better point, I can sort of say, well, you know what, I know that this velocity here is not, it's 3 meters per second, but I also know this velocity here is 0. And so another technique we'll be talking about in the next couple lectures, I'm not sure if I'll talk about it today, is instantaneous centers of zero velocity. But if I write it as a vector form, I can say right away, because this is rolling without slip, in kinematics in chapter 5, we tell you what's happening. In chapter 6, you worry about what's happening. But VA equals VA with respect to C. And then it's a rotation. We already know omega. And the omega that I calculated over here and over there and everywhere is the same on a rigid body. So no matter what I do to the angular velocity, or no matter how I calculate it, any point on the body will have the same angular velocity. So if that's the case, then it's omega cross r, or omega r, since I'm doing it as a graphical approach. And VA with respect to C equals AC omega, which is AC OC V naught by triangles, and it equals, no surprise, 4.36 meters per second. Because in this particular case, the rotational velocity is the same as the rotational velocity of the body can give you everything you need. And so this idea of using a 0 point is an instantaneous center of zero velocity. And just for completeness, I'll refer to it later. This way, ICZV. There we go. So what you're looking at here, and I'll try and do another example like this, not with absolute dependent motion because I don't care about absolute motion. I will do another example where I look at graphical and vector approaches. One of the things that you should be doing before Monday is trying to do one of these problems, whether it's the ones in lecture, the ones on the exams, anything, just to get comfortable with whichever approach you like better.
Could you explain that last one?
Which one? This one? So this one, all I did was say, hey, I can define everything with respect to velocity of A with respect to C. Okay. So instead of doing this, I can say velocity of O equals to OC omega. Velocity of A equals AC omega. Both of those have the same value, right? For omega. So omega is equal to V naught over OC, which equals VA over AC. And then I can do similar triangles. It means that I take a few less steps. I'm not a big fan of this either, by the way. I think this is a great technique in the right circumstances. It's not a great technique if you try and sort of force it into every possible problem you face. It's better sometimes to sort of take the hit and sort of say, okay, I'm going to do everything with respect to O and not look for that ICS or ZV. Any other questions on this? So again, as much as possible, try to go through examples of this nature and understand how you're getting these graphical solutions to work. There we go. Now, this is kind of a useful problem, and it's one I've done for years. I kind of like it. I have a system which consists of a belt. The belt is attached to A and point C. So this is essentially a gear. You'd see this in a transmission, something of that nature. And on the center of it, you have a center D, and this mass B is attached. And again, we're dealing with kinematics. We don't care about the forces. We don't care about how this is happening. We just care about the kinematics. The radius of A is given as 50 millimeters. The radius of C is given as 150 millimeters. The radius of D is 75 millimeters. Starts from rest, and you know that alpha is equal to k theta and k equals 6 rads per second squared. What is the speed of block B when it rises 6 meters? So you have a couple things that you know. So I have a belt, and I've attached it. There we go. I've attached it there, and what I know is that any point on that belt is going to have the same velocity. So as it rotates, or as it moves around these two gears, if it's going at the top at 1 meter per second, at the bottom it's going with 1 meter per second. However, on the gear C and D, the radial velocities are the same, and so omega is the same, but v, the linear velocity of C, does not match the linear velocity of D. All right, so if I look at points C and A, those points of contact, I can say that the displacement of A is the same as the displacement, linear displacement, measured in meters, of C. So I can look at the arc length of both and say, well, theta A RA equals theta C RC. And if I go a little bit further, I can take the time derivative of that and say, well, RA omega A equals RC omega C. So both of those have the same are different. They have different omegas. They have the same velocities. So maybe I'll do that a little bit more explicitly. Now the other thing is there's no time derivatives on RA and RC because those are not changing with time. So RA stays constant, RC stays constant. So putting everything together, I get omega C is equal to omega A RA with respect to RC, or divided by RC, sorry. However, if I look at the other part of the system here, C and D are rotating, and both of them are pinned at the center, and they have the same angular velocity. So omega C and omega D are the same. Velocity of C and the velocity of D are not. And the angular displacement of C is just going to be the arc length traveled divided by RC. All right, so that's okay. And that will also be SD over RD. Oh, I think I didn't tell you what theta C was. And that is equal to 80 rads. Oh, wait, no. You don't need to do that. Okay. So, sorry, I should have been more careful with that. So S sub D is given in the problem. That's that K value. That's the, 6 meters. And this is 75 millimeters. All right, so you're given enough to sort of work out what the angular displacement of C is. Now, separately, because you know the relationship between linear velocities, you know that alpha A is equal to K theta A, and we need to know theta A. Ooh. So theta A is equal to RC divided by RA theta C, which equals 3 theta C, which ends up being 240 rads. Okay. So based on that, I know how much rotation has occurred on the wheel A during this rise of 6 meters of the mass B. So I got the 240 rads, I've got all this. Let's keep going. I can do the same thing. I know I have a constant acceleration, or I have a term, not a constant acceleration. I have K theta. What is it? It's, alpha A is K theta A, but I have an expression for that, and I'm going to have to do an integration. So this goes back to your fond memories of section 2.2 of the book, where you did this with linear velocities and accelerations. So it's the same thing, but it's just written in this form. And again, rads per second, rads per second, rads per second over rads. Now the difference is, of course, that I can multiply and divide as many rads as I want to, and I don't make a rad squared or a rad cubed. Over 2. Now, I can then calculate, based on this, I have theta at the initial point, which I'll set to 0. I always will do that. I could do this as a delta, but that's OK. And omega at time 0 is equal to 0. So I end up with this relationship between the two, ends up with a half, and I get rid of that right from the beginning. So now I have omega A, and I have omega D. And omega C, by the way. And if I want velocity of D, it's straight from kinematics, 195.6 rads per second. Now, I'm not doing any of the unit conversions in the problem. I'm just writing the units down. I do this because it's not really worthwhile doing very much. But if I were checking this problem, I would immediately see, for example, I have millimeters. Any questions on this?
Could you quickly just show us which values we were given?
Yeah. These. So you were given the radii, RA, RD, RC. I think there's no B. You were given that it starts from rest, and the one thing I didn't say is that it's alpha A, not alpha. And k is equal to 6 rads per second squared, so you're given that, all of that information. What is it, the speed of the block after it rises 6 meters? So the important things to understand is that in order to translate a linear velocity to a rotational velocity, you need to have it at a point on the body. So typically when I deal with belts, I'm going to assume that the velocity of point C is the same as what I've called velocity of A. And the point A is the same as velocity of A. Which means that at this point and this point, I can say velocity of C equals velocity of A, and RC omega C equals RA omega A. What I can't say is that omega A equals omega C. However, when I look at D, C, omega D equals omega C. So this is a really nice problem in the sense that it shows you all of these things in one sort of fell swoop.
Just a quick question. For other points on the plate themselves, would we be able to say that VC equals VA2?
So any point on the pulley, I wouldn't call it VC, VA. I'd just call it VA because I have it defined that way. So this point, for example, has a velocity of A. And ideally, it would be just velocity of the belt. So I would call it velocity of the belt. Velocity of A equals velocity of the belt. Velocity of C equals velocity of the belt. And then the linear velocities are all the same all over. This is not the best way for me to write it.
But like on the pulley themselves, it's also the same speed, but not like the same direction.
Yes. So on top, based on the way I've drawn this, velocity of A is going in this direction. On the bottom, velocity of A is going in this direction. And you're going to spend a lot of time, this is where things get fun, with gears, where you'll have things that are rotating and meshing together, where you'll have sort of a point of contact with no slip between two gears, and things will depend on the radii between the two gears. Yeah. So you're going to spend a lot of time on this. Please, please, please know the definition, know how to sort of use this. Excellent. Okay, I can't say this enough. There are two choices in every approach or every example that you do. What you need to be able to do with all of your problems, and I haven't been as good at that so far as I should be, you'll see it on the diagram, is make sure that if you're dealing with a velocity, draw the velocity out. Show what the velocities are, no matter how you calculate it. If you do everything correctly, it'll work out really nicely. So, of course, oh no. I have a slider, and that's at position C. I also have a pinpoint, and these are going to be very important. So if I look at this system, or this mechanism, I have AB, which is rotating about point A. I have BC, and I have point C, which is a slider, and it's moving left or right. I don't know what at this point. And one of the problems I have intuitively doing these problems is sometimes things don't work out the way I think they should. I think in this one it sort of does, which is good, but okay. I probably should change the directions. All right, so I have at the top translation. At the bottom, I have a rotation, and in between, I have general plane motion. So if I sort of write this out a little bit more, AB and C So I have all three types of motions that I've described here, but one of the things that's really important to realize is that I can only do the analysis on one rigid body at a time. So if I'm looking at AB, I can't tell you anything about C. If I'm looking at BC, I can tell you, no, I can't tell you anything about A. But any point that is common between the two rigid bodies has the same velocity. So the velocity of B on the link AB and the velocity of B on the link BC is the same. So velocity of C equals velocity of B plus velocity of C with respect to B. Same thing as before. The approach I'm going to take with this one, and I will not finish it today, we'll finish it tomorrow, is to do it first as a vector solution and then as a graphical solution. All right, I'm given theta and phi of 45 degrees. Length of AB, which is that link A, or the distance A, is 300 millimeters. And the length of BC, which is little b, is 125 millimeters. So let's start by looking at AB on this. I've got A, I've got B, I've got a rotation which is given to me as 4 rads per second, and it's counterclockwise, which makes it a positive value. So it's rotating about point A because it's a fixed point, and I can start to do a little bit more with it. Ew. I need this. So if I'm looking at point A or point B, I can create a triangle right away, which is A cos theta, A sine theta. And if I do that, I can say that velocity of B equals velocity of A plus velocity of B with respect to A. Okay, so that's all there. Good. Velocity of B equals velocity of A plus, and one thing I know right away, because this is fixed point rotation, it's rotating about point A. Point A has 0 velocity. And so if I solve through, I can say velocity of B is equal to omega AB crossed with RB with respect to A. But I've already written out all of the terms that I'm going to need for that expression. So as I'm looking at this, I only have rotation. Now, I have VB, so for velocity of C, I know what velocity of B is. Because velocity of B on BC is the same as velocity of B on AB. A common point is always a common point. And sort of parenthetically, I also know that when I solve through for this, it'll look like this. Maybe I don't want to do it that way. Now, I know that because I have fixed point rotation, but I'm going to make sure of that when I start to look at what the answers are that I get out of my problem. So I got A sine theta, A cos theta. I've got the distances from A to B. I've got V sub B. I also have the same problem with C and B, but when I look at that link BC, I have B cos phi and B sine phi. So one of the things I should do right away, and I didn't do at the beginning, is to put my xy coordinates. So my A cos theta is good, my A sine theta is good, B sine phi is good, it's all positive. This one is negative. So point C with respect to B, you have to go back a distance minus B cos phi in order to sort of fill it in, or to sort of get your x coordinate. So at this point, I can sort of say my original equation, which was VC equals VB plus VB relative to C, or C relative to B, I can start with V sub C, 0, 0. So my vector for V sub C is constrained to the I direction. It's either positive or negative. I don't know. I don't care at this point. I just know that I will not get a VC that acts in the Y direction, and none in the Z. Never for linear velocities in this course. So I can rewrite all of those terms that I've already calculated because I have everything I need. So in terms of what I don't know V sub c, and I don't know omega bc. And if I solve through this problem, I'll get two equations. And I'll end up with omega bc, which is equal to 9.6 k rads per second, and velocity of c, which is equal to minus 1.7 meters per second in the I direction. I don't need to know anything about the directions of the velocities at this point, other than that everything should go in a certain way. I do need to know the positions of vectors in order to solve things. So I can solve easier by drawing on my diagram a cos theta, a sine theta, minus b cos phi, and b sine phi. And we know omega